Hi everyone, today's lesson is going to be covering GCF, which stands for greatest common factor. Here in this list we have some review, vocab. You can read through that on your own. The main thing we're going to focus on is greatest common factor, so GCF. The definition of that is if you're trying to find the greatest common factor of two or more integers, it's the greatest number that is a factor of all the integers. What that basically means is if I'm comparing two numbers like, let's say, for example, negative 45 and 15, I want to find the biggest number that I can divide both negative 45 and 15 by evenly. So the way we can determine that is by listing out the factors of 15, and we're going to list out the factors of 45. We essentially can ignore the negative sign here because we want to find the factors of that positive value of 45. That would be the greatest common factor. So for 15, I know that I can use 1 times 15 to multiply to give me an answer of 15. And I can also use 3 times 5. And I wrote them in that order just because I like having it in a list from smallest to largest number here. So 1 times 15 or 3 times 5. Those are the factors of 15. So there are 4 factors there that we can choose from. Now, to find the factors of 45, I know I can start with 1 and 45. I know 2 would not evenly divide into 45 since it's odd, but 3 does. 3 and 15 are factors of 45, 3 times 15. And then the last set would be 5 times 9. So that would complete our list there. Now, between these two numbers here, 15 and 45, I can see that the ones match up. They both have a factor of 3. They both have a factor of 5, and they both have a factor of 15. Our task here is to determine the greatest common factor. So they have, let's see, 1, 2, 3, 4 common factors. But the greatest one is 15. So that would be our answer for the GCF of those two numbers. So that's the basics of finding the GCF of two integers. Today we are going to bump that up and turn it into algebra by adding in variables. So we're going to practice finding the GCF of numbers and variables now. So at the top of the next page, you're going to see the greatest common factor for the same variable will be the lowest exponent of that given variable. This is kind of the trick that we can use to find it really easily when we're trying to find the GCF of a variable. Okay, so I will do some examples here in example 3. Starting with A, x squared, x to the 5th, and x to the 4th. Our task here is just to find the GCF for each set of monomials. So we have 3 different monomials here. They're each just one term because there's no plus or minus signs in there. And we need to find the greatest common factor for this set right here. All right, so using our trick that we were given at the top, we're going to choose the lowest exponent of that variable. So that means the GCF of these 3 monomials would be x squared. The reason that that works is if I wrote these out as expanded multiplication. So x squared would be x times x, x to the 5th, I would multiply it 5 times, x to the fourth, you would multiply x 4 times. Basically, you're looking here for the greatest common factor to be how many x's you would be able to evenly take out or divide out of these groups. So here, there's one x that we can factor out, and there's a second one. But since this first monomial only had 2, that's the most that we can factor out. So that's why it would be the greatest common factor would just be that x squared. So we're used to, or we've previously been doing a lot of multiplying polynomials and multiplying binomials. Now we're like thinking the opposite direction. Now we're thinking division. What can I divide out, or what can I take out evenly? So we've got to like switch our mindset here. All right, so let's look at B. We have 49x and we have 343x squared. So when we're trying to find the GCF with a coefficient and a variable now, we're going to start by finding the GCF of the coefficients. When there's a large number like 343 involved, I usually start, when I'm trying to find the GCF, by dividing 343 by 49 in hopes that that would divide out evenly. And it does, because 343 divided by 49 is 7. So that means that for sure the GCF of 49 and 343 is going to be 49. And then we move on to the variables, x and x squared. So the lowest exponent would be 1 right here. So we can take out an x, and that would be our GCF is 49x. On example C, we've got 4a to the 7th b and then 28ab. So to identify the GCF for this one, we're going to start, of course, by finding the GCF of the coefficients, 4 and 28. 4 is a factor of 28, so that's going to be the greatest common factor. 4 divides evenly into 28. Then we'll check the a's. So we have a to the 7th, and a is the lowest, so that's going to be the common factor. And then they both have a b. There's a b here, there's a b here. So the greatest common factor between b and b is b. And then example D over here, we have 96y, 12x, and negative 8y. So we're going to check first for the GCF of the coefficients. Now, I usually take that smallest coefficient and try to see if I can divide that into the other factors. I cannot divide 12 by 8. That does not work out evenly. So then I'm thinking, okay, well, what's another factor of 8? That would be like the next highest factor of 8. That would be 4. And I can for sure divide 12 by 4 evenly and 96. So that means the GCF is going to start with 4. Okay, then we want to check the variables. The first term that's listed here in this list is y, and then as I check the other terms right here in the second one, there is no y there, so I can't divide out a y because there isn't one. Dividing x by y would not accomplish anything there for us. So our GCF won't have a y in it, and it also won't have an x in it because these two terms don't have x's at all. So since there's no more common factors or common variables here, our GCF just ends up being a 4. We could only, that's the most that we could factor out of these 3 terms, would be just a 4. So that process right there will get us started for the act of actually factoring. Up here, there's the definition that I skipped earlier because we hadn't gotten to it yet, but factoring is means to express a polynomial as the product of a monomial and a polynomial. So now that we're factoring, our answer will look like a product. Well, I'm going to use some space over here. If you guys think about what we spent a lot of time doing in the polynomials unit, we would start with a problem that might look like 3x times x squared plus 5. We would start here, and then we would have to multiply, so we would do our distribution, and we would get an answer of 3x to the third plus 15x. Now that we are factoring, we're working backwards. So we actually start with this. If you look at all of our questions in this next section, they start as a polynomial, no parentheses or anything. They start as a polynomial, and we'll actually get this as our answer. So it's kind of like we learned how to multiply, now we're unmultiplying, which is probably a word that doesn't actually exist. But that's the idea, is that we are undistributing things. So when we're factoring, we start with a polynomial that looks like this, and then we will factor out or divide out as much as we can. So we're going to start with example A, of course. In this last section down here, and our first step, so this process will be the same for each of these examples that we do. Our first step is going to be to figure out what's the GCF. All right, so I look at both terms, and right away I can tell this one has a W and this one has a Z. Those letters are not the same, so I'm not going to be able to factor out a variable. But 24 and 72, those share factors. They share quite a few, actually. But 72 divided by 24 is 3, so that will be our greatest common factor is 24. You can divide both by 24 evenly. Okay, so that's just the first step. That's what we just practiced in the 4 above this. Now we're going to actually factor and get an answer. So to do that, we're going to take 24, and behind it in parentheses, we are going to write what I like to call the leftovers. What that means is I'm going to divide both terms by my GCF and write what's left over in the parentheses. So here, 24 divided by 24, that's just a 1. So we don't really need to write 1 times W. So this term just has a W left over. And then 72Z divided by 24 would be 3Z. So that answer right there would be the factored form of this original polynomial. Now, the good thing with these is you can easily go back and check your answer by distributing. And you can probably see here without even writing the answer down that this would give us 24W plus 72Z. So just to make sure we've got the steps here, we're going to write the GCF or find the GCF, and then we're going to take the GCF times the leftovers in parentheses. I'm sure that's the official term for what we put in the parentheses. Okay, so I'll do a few more examples in this video, and then I will cut it off, and you can practice the rest and then check with the key later. So let's do B. 30ab squared plus a squared b minus 12ac to the third. So I want to look through my three terms, and first I always check for the GCF of the coefficients. Those are 31 and negative 12. Since this middle term doesn't have a coefficient, I can't factor out a coefficient. So then I'll move on to the a's. A squared, and a. So I want to think, what's the most that I can take out of that variable, and that would be just an a. Then I want to look at the b's, b squared, b, and then, oh, there's actually no b in the third term. That means I can't take out a b if there's no b there. Same thing with the c. This is the only term with a c in it, and the other two don't even have a c. So our GCF ends up being a, which might be deceiving when you first looked at it because there's a lot going on in this polynomial. But the GCF is just an a, so that's all we can take out. So we put that GCF first, we put parentheses after, and I like to go through and show that I'm dividing out that a, so it makes the leftovers even more apparent. All right, so when we divide in the first term right here, a divided by a, that's just 1, so those cancel, and that gives us 30b squared. The second term, we're going to add on right here, a squared divided by a. The division of just an a would leave a in the numerator times b. Remember the quotient rule, we like subtract those exponents, so that would be 2 minus 1. So you're left over with just 1a times b, and then the third term, the a's cancel again. So that would be 20c to the third. I would like to leave C for you to try on your own, and you can check it with the key later. And I want to do D next. So let's do that one. All right, so the GCF, this one has two terms, A and then all that. Well, this only has an A in it, so our GCF is going to be A. That part might seem pretty obvious, hopefully. So A would be the most that we could take out of either of these terms. Now when we go to write our answer, A and then parentheses with the leftovers. A divided by A is 1. Yes, they cancel. When things cancel like this, that means they become 1. So I want to go back up here real quick. When these canceled, those A's canceled, because there were other pieces to the term, we just wrote those other pieces. But in reality, when we do A divided by A, that's a 1. So that means like we were multiplying 30 times 1 times b squared. And we all know that it's not necessary to write times 1 in a polynomial term like that. For this one, the difference is A divided by A was the only part of that term. So we have to keep that term and show that there's value there because A divided by A is 1, it's not 0, so it doesn't just disappear. So we have to show, that there's a 1 there, and then plus 10ab to the third. So one of the a's cancel in the second term. But I wanted to show you that one specifically because sometimes we go really fast and we're like, oh, a cancels, we don't write anything. But since it's the only piece of that term, we do need to show that term. So we put a 1 there. Anytime we're writing these parentheses, here, if there were 2 terms in our original problem, there's going to be 2 terms here. We had 3 terms in our original, we had 3 terms in our parentheses. So that's another checkpoint that you can use for yourself. Okay, I'm going to let E and F be problems that you do also on your own. So C, E, and F. And also G. And then we'll talk about the last 4. So I'll do these real quick. So H, this one has 4 terms. The process is exactly the same as we did up above. So I'm going to look at each term here. Already I can tell I'm not going to be able to have a number as part of my GCF because some of these terms don't have coefficients, but I can definitely factor out an x. I want to make sure I factor out as many as I can. So remember, we'll check the exponents, and 3 is the smallest exponent, so x to the 3rd would be my GCF. So that goes in the front. And then you don't have to write this like division part every time, but I think it's a good visual to make sure we do the quotient rule properly. So the first term that remains here would be negative x squared. And then minus 4x. There would be 1x left over there. Here, 23x to the 3rd over x to the 3rd. That leaves you with 23. And then minus x to the 3rd. Another helpful checkpoint would be to look back through, especially because there were a lot of x's in this one, to look back through and make sure that you wouldn't be able to factor any more. So like if I had accidentally done this wrong, and I'm going to use red because you know that way you know it's wrong. If I had accidentally done this incorrectly and I saw an x here maybe behind the 23, I would have to say to myself, oh wait, I don't think I took out the GCF because there's still an x in every term. So you want to make sure you took out the greatest common factor. Make sure that when you look back through your final polynomial, there's no like remaining common factors there. And then these last 3 are kind of some special case scenarios here. So looking at I, 8x minus 7y plus w. You might already be thinking like, huh, that seems weird. That's because this one does not have anything we can factor out. I can't take out anything from coefficients, and all these letters are different. So this is prime, or you might say it can't be factored, or I'm thinking of like ways it might be given to you in a multiple choice question. You could also just rewrite the problem and box that as your answer because that is the answer. Okay, and then J and K are 2 special cases. I'll definitely talk about this again in our next class, but I'm going to look at K first. When we go to factor out the GCF of K, the GCF would be an x. That's what those 3 have in common. So I would put x out in the front, and then when I take that x away, we have x squared plus 2x plus 1. We talked about this being 1 earlier. The reason this is a special situation is because this right here, this form that this polynomial is written in, hopefully once I say it will look familiar, but this is in this is in quadratic standard form. So we learned that quadratic standard form, is ax squared plus bx plus c. So when we have quadratic trinomials like this that are in this quadratic standard form, we can actually factor this further using a method that we're going to learn on Friday. So this would technically not be correct if I stopped right here, because we should continue to factor this. We can break this down even more. Same thing with j. If I take out the GCF of j, which 18 and 50, the greatest common factor between those is just 2. So if I take out the GCF of this one, 9y squared minus 25, this is like a super special case of a quadratic function, but it can also be factored further, and we'll learn how to do that on Friday. So j and k can be factored further. So it wouldn't be completely correct for us to just like stop here, box that on our answer as our answer and be good. But on Friday, we're going to learn how to completely factor these. So that's why I'm like circling them, because they're not complete yet. So we will learn how to do that on Friday. All right, so these problems that I've circled, I would love for you to do them on your own and then check with the key on Canvas later. And that is all I have. So have a great day.